Welcome on this episode of Tomorrow's World Today. We visit the world of production to learn about how to make semiconductors that can work in space. We explore how one company is taking a bite out of wafer production by mimicking extraterrestrial conditions right here on Earth. From Invention Land World Headquarters, here's our host, George Davison.
Hi, everybody. Well, a semiconductor is something that can conduct electricity under some conditions, but not under others, which means it can control the electrical current, basically. Similar to how I can turn this switch on and off with the press of a button. But what if you need something that can move the energy a little faster, right? Well, if you're lighting up many different lights or turning on a lot of machines, you're gonna need something more like this motherboard. And what this is gonna do is to help to direct the current. And every time I turn this switch, it's gonna move another cluster of lights. As you can see, they're coming on. And they're getting more and more complicated as I go. This is where a semiconductor comes into its own. Let's take it one step further. This is a wafer, which is a type of semiconductor used in everything from phones to satellites to even our spaceships. In fact, many of the wafers, similar to this one, were used on the Mars Perseverance rover. Once the wafer leaves Earth's atmosphere, it may be exposed to extreme temperatures, different climates, and even space radiation. Space radiation is made up of high-energy particles and heavy ions released during solar flares, or during other equally explosive events outside of our solar system. Without Earth's magnetic field to deflect space radiation, electronics are vulnerable to its destruction. So you have to make sure that that wafer that you're using can handle these most extreme environmental situations. Plus, they have to be reliable so that someone running them here on Earth knows that they're working out there in space. Now, let's catch up with Greg, who's over at CASE to learn more about semiconductors in space.
Thanks, George. I'm on the case, or should I say, I'm at CASE in Colorado Springs to learn how they're making semiconductors for use in missions in outer space and how they're tackling the Achilles heel of semiconductors, radiation, all the while making them reliable and able to withstand the harshest conditions. CASE is the leading provider of radiation-hardened technology to the aerospace and defense industry. Let's go inside now and meet David Mayuhas. He is the Senior Director of Standard Products in the Space Systems Division. Hi, Dave. It's great to meet you.
Hey, Greg. Welcome to CASE in Colorado Springs.
Thanks for having me. This is a really exciting time to be here with everything that's going on in space exploration now. This is a great time to check out your facility. One of the things I was really surprised about in doing research for your company is that you've been doing this for 35 years.
You're absolutely right. In fact, we started off in the early 80s developing semiconductors for the aircraft engine control systems. And we saw an opportunity to really elevate the altitude for where our products went, and we're higher than space. So we started developing radiation-hardened microelectronics based off of semiconductors, and haven't looked back since.
That's amazing. I can't wait to find out more about it.
We've got a lot to talk about. Let's head on over to the mission control room.
Let's go.
Greg, I'd like to walk you through a bit of a journey for CASE's contribution into space. It all starts off with the sun. What we think here on Earth of the sun, warm sunshine, is actually radiation bombarding the Earth. Now, we're protected by it because of the magnetosphere. But once you send electronics up into space like satellites, they don't last very long. That's what happened in the 80s and 90s, where we had satellites fail after 6 whole days.
Wow.
Big investment to have that fail after such a short amount of time. When we saw this, we saw it as an opportunity, our eureka moment. We had to get our engineers to figure out how to solve that problem. So our engineers immediately started working on injecting radiation hardness DNA deep into the semiconductor circuit. Our first product that was radiation hardened actually went on NASA's SAMPEX mission, and it was initially only designed to last for 3 years, but lasted for 20.
Wow.
Over the years, we had many contributions through the spacesuit, the space shuttle program, International Space Station, GPS, which we all know and love today, Juno, and then finally something more recent, the Mars Perseverance rover. This is a contribution that CASE, pioneering advanced electronics across the years, has been able to implement a ton of content on there, whether it be our processors, our memory, radio frequency devices, power modules, waveguides, motion controls, it's all in there. But back down to Colorado Springs, let me take you to see Rich and see how we manufacture integrated circuits.
Sounds great. The environment in space is much different than the environment on Earth. And if we're trying to power everything from satellites to spaceships, we have to take that environment into consideration. So far, we've learned about how radiation is the Achilles heel when it comes to creating something that can handle the harsh elements. Now it's time to learn more about how semiconductors that can handle space's environment are made right here on Earth.
So Greg, I'd like to introduce you to our manager of process engineering, Mr. Rich Miesmer.
Hey, Rich, nice to meet you.
Nice to meet you, Greg.
So Rich will be walking you through our clean room where we manufacture and assemble all of our radiation-hardened semiconductors.
Sounds great.
You're in good hands.
Thanks a lot, Dave.
So, Greg, there's some things you need to consider when making something space-ready. Any idea on what you might consider?
I would think a key consideration would probably be the atmosphere.
You are correct. Other things to consider are keeping the contaminants from Earth out of the package, so we don't take those to space and potentially damage the package as well.
So I guess that's why we're going to go take a look at the clean room.
That's correct.
All right, let's go take a look.
Follow me? Hi, Greg. Want to welcome you to the clean room?
Great.
I'd like to show you a wafer being cut, and then we'll walk through the assembly process.
Okay.
So we've just seen the wafer being cut.
Right.
So now I'd like to show you the singulated die
Okay.
as we go into the manufacturing process.
So this is how it comes to you from the cutting process.
That is correct, yes.
All right, show me what happens next.
All right. All right, Greg, so now we're going to show you the manufacturing process.
Great.
So right now it's dispensing epoxy
Okay.
on the die. This will help hold the die in place through launch conditions, which might have vibration, constant acceleration. Now we're picking up the die, and it's going over the red light,
All right.
verifying proper orientation, and placing it onto the epoxy that we just dispensed. Then the next step would be to connect this to the outside world through the wire bond process.
Okay, can we see how that's done?
Absolutely, let's go.
All right. Tell me what's happening here.
Right now we're ultrasonically bonding the wire between the die and the package itself.
And this is basically how it's going to communicate with the outside world.
Correct, so the wires are allowing us to have functionality between the package and the die.
All right, great. What happens next?
From here we'll go to lid seal.
All right, let's see it.
Great.
So, Rich, I see you have a new piece of equipment on there. What's that for?
This is an ESD strap. This is going to protect the package from electrostatic discharge.
And I know that's important because electrostatic discharge, it can damage chips in a way that you might not know for years.
That's correct, Greg. And now I'm attaching the lid to the package and clipping it so that we can go to the seal operation to form that hermetic seal before it goes on and shipped into space.
It's nice to see that with all of the automation that you guys have going on here, that this is still done by hand.
Yes, this is one of the few remaining manual processes. Now we're ready for the lid seal process.
Let's go see it.
Great, let's go.
So, Rich, this is totally cool. You're going to have to explain to me what exactly is organic burnout.
So during the die test process, there may have been some organics left on the die itself. So this is going to burn those off and seal the package at the same time.
You're ready to go test it and get it up into space?
That's correct. On to test after this in preparation for space.
So Rich, we sent this through the organic burnout machine and that seals the lid properly, but now we need to test it.
Yes, so what we're going to do here is test to ensure that we don't have a path for moisture to get in, and so we can keep contaminants out of the package for when it goes into space. After this, we'll go and we'll test it at minus 65 C for temperature extremes.
Let's do it.
Let's go. Let me put you to work.
I'm ready.
Let's go ahead and place this into the temp cycle chamber.
Okay.
And once we get done testing at the extremes, then we'll run the final test to ensure functionality of the parts.
Well, let's head over there.
Let's go. So Greg, now that we've completed stress testing at hot and cold, it's on to final electrical test.
All right, can you tell me exactly what's happening here?
Sure. What we're doing here is we're performing electrical tests on semiconductors at room temperature. However, we will also perform it at the temperature extremes. So let's see how we can take what we've just learned and apply that here on Earth.
Let's do it.
Let's go.
Our testing is extremely aggressive. I like to say we're beating the crap out of the parts for 6 to 12 months, putting it in an oven, putting it in a freezer, cycling the temperature, exciting it electrically, making sure that you test the entire gamut of that product for months on end to really ensure that it survives at the end of that test process. And that helps guarantee and assure that in space, when it would see similar conditions, it would continue to function as designed and as intended.
We've learned how semiconductors used in outer space have to be ready to handle harsh conditions. But everything that they've done to help with space missions can also be applied to us Earthlings too. So Rich, it's pretty obvious that every semiconductor that CASE makes doesn't end up in outer space. What can you tell me about what CASE does to help us more Earthbound folks?
So have you ever had an X-ray or a CAT scan?
I've had an X-ray.
Okay. Well, similar to space, with the radiation, those devices will also emit a radiation.
So basically anything designed, built, and tested to go into outer space is going to be able to withstand the rigors of the healthcare industry.
That's correct, Greg.
All right, great. So tell me about this machine.
So this is a pick and placement machine. It's taking components in these reels here and putting them on substrates.
So each one of these little dots is an electrical component.
That's correct.
That's amazing.
And in the smaller reels, you have upwards of 10,000 components, and in the larger one, closer to 50,000.
How exactly do you affix the components to the chip?
So we will put solder paste on it. That helps hold the components as it's going through the line. Once components have been placed, we'll put them in here, and that will reflow the components and secure them to the package.
So it's a little like the organic burnout machine we saw earlier.
Correct.
All right, great. So this has been fascinating. The clean room is amazing. I have to admit, this has been a blast. But I have got to get out of this stuff. Can we go see some boards being built?
We can do that. Let's go this way.
Let's go.
Radiation isn't only a concern up in space, it's also a concern here on Earth. If you've ever had an X-ray, those same radiation elements that you would see out in space are also seen inside the hospital. And so it's important that the electronics within X-ray equipment are also designed to be able to be tolerant or resistant to radiation.
So Rich, we've done the testing. Can we build a board?
Yes, in fact, the board build starts right here. First operation is to print the paste on the board.
Okay. And this unit is very similar to the one we saw in the other room.
Absolutely, Greg.
What happens next?
And after that, then we go in and we inspect the paste to ensure that the right volume has been placed onto the board. Once the paste has been applied, then we'll come around and we'll start adding components through the SMT line.
Now this is really similar to the other device that we saw in the other room. It's basically putting the same kind of components, but now on a board rather than on the chip itself.
You're correct. And then we're going to move to the next system, and those packages that we were building in the clean room, that's where we're going to apply those to the board. So once the chips are on the board, then it's going to go in, we're going to perform an inspection on it. And what we're doing there is we're ensuring that they've been placed properly, they're rotated correctly. If there's any other criteria mark-wise, we want to make sure that that's correct on there as well. Once we're complete with inspection, now we want to make sure that the components are fixed to the board, so we're going to reflow it together.
And this is similar to the unit that we saw over in the healthcare division.
That's correct, Greg.
All right, now, I imagine once these things are all put together, you don't just wrap them in a little bit of bubble wrap and drop them in the mail. Shipping's got to be a real thing here.
Yeah, so you are correct. We will not put it in bubble wrap. It will go into a specialized container, and that'll get sealed, and then it'll be shipped.
Okay, can we see that happen?
Yes, let's go see it.
Let's go take a look.
So Greg, we've made it to final pack. Here's where I'd like to show you how we take the semiconductors we've been following and get them ready to ship. As you can see, these are matrix trays, which are designed for the package. That's going to help keep them secure and stationary while we ship. We'll secure the matrix trays with rubber bands so that those don't shift either. And we'll place them in a box, and that'll keep everything secure.
Great.
And then when we're done and ready, we'll place it in a moisture barrier bag to keep moisture out during shipment, and it's all set.
And this thing looks like it's worried to be sent into outer space.
You got it, Greg.
Rich, this has been amazing. Thank you so much. I'm heading back to Invention Land. We'll see you soon.
Thank you, Greg.
Hi, David.
Hey, George.
Thanks for coming all the way in from Colorado Springs.
Thanks for having me. I gotta tell you, we had a great time showing Greg around our manufacturing site, talking to him about how we design and build semiconductors for space.
Well, that's a good segue. Space. So tell me, what's the future of space and your organization?
Future of space is all about chiplets.
Chiplets.
Chiplets, think about it as a big cinder block where you're trying to jam in all that capability, all that computational prowess into one cinder block. What chiplets do is they break that cinder block up into smaller chiplets, like building blocks that your kids used to play with.
Okay.
And what that does is enable us to take each one of those building blocks that have the most capability and build up an entire system that our customers can modulate and customize depending on their mission or their spacecraft or their satellite or their rover.
That's a big innovation. So I'm able to pick and choose almost standardized chiplets and build them up in accordance with the needs that I have for my particular mission.
Absolutely. In fact, I have an example here for you.
Mm-hmm.
These two elements right here, these are two individual chiplets. And depending on the configuration or what mission the customer is trying to solve, you could add additional chiplets at the bottom.
So those 4 golden squares there are additional capacity that I can get to?
That is a space for us to add additional building blocks or chiplets to the system.
Well, that's pretty wonderful. So in other words, I have expandability if my project is different than your project, and I can use these basic building blocks. I can go off in my own direction and not have to customize everything. Is that
Correct.
correct?
Scalability, leveraging the latest and greatest technology for each application.
That's wonderful. Great innovation, David. What else do you have for us today?
Great question. Here we have our actual first microcontroller that went up in space out of Case in Colorado Springs. This was the one that was initially designed on the NASA SAMPEX mission. That entire mission was intended to only survive 3 years, but lasted 20.
20? Wow, that design team did a great job now.
They sure did. They sure did.
Well done.
Moving on, we also have our latest generation microcontroller. Now, just take a look at the size difference between the one that was designed in the early 90s and the ones we have today. And we have even more computational power or capability loaded into that small chip, and it draws less power. It's really just a magnificent example of innovation for semiconductors over time. You're able to make it smaller, you're able to get more out of it.
Well, if you're only using a solar panel up there, you don't want to consume more energy than necessary.
Exactly.
That's
exactly.
big. That's a big one.
Finally, pièce de résistance, our Leon microprocessor. This one, we actually have a replica of it, but it's up on the Martian surface on the Mars Perseverance rover. It's helping out with lab experiments to help convert CO2 into oxygen with the intent to eventually have oxygen on Mars. As you know, if we ever want to inhabitate Mars, it's going to take some oxygen up there.
Count me in. I want to be on the first group to go up and breathe on Mars.
I'd like to help you get there.
All right.
Oh, by the way, these are for yours to keep. It's Case's gift to Tomorrow's World today for you to showcase
Oh, thank you. Well, you know what? That's going to work out great because we get thousands of kids through here. We'll put a showcase together for Case and put the chips in there. We'll tell a story of innovation in space. How's that sound?
I love it.
All right. Well, thanks for coming in.
Thanks for having me. Take care.
Bye-bye.
What do I see leveraging chiplets onto the next 30 years? Really taking our pedigree and our history of robust, reliable, radiation-hardened design, bringing that over to chiplets and really helping enable space exploration, new space constellations around the Earth, and really just expanding humanity's reach into extreme environments.
We hope you've enjoyed learning about semiconductors in space on this episode of Tomorrow's World Today. For Tomorrow's World Today, I'm reminding you that new ideas are the source of innovation. What will you do with yours in tomorrow's world? Today.